Hi everyone. In our next video, we will be going through section 6.2, and that is the binomial probability distribution. That's the section we're on here. And what the binomial probability distribution is one that is expressed with a formula. That's the best way to represent the binomial probability distribution, and we'll see why as we go through the first our first example in the section in a little bit. First, though, we'll go through the criteria, what it means for something to be a binomial distribution. Binomial, if you think back to high school algebra, there's two terms. For a binomial experiment, for each trial, and I'm looking at number 3 first, there need to be two mutually exclusive outcomes. That's why it's binomial. There's two outcomes. So, like rolling a die is not a binomial experiment because there's 6 different outcomes. Okay. But the second criteria, the trials need to be independent, which means that what happens in one trial can't influence the next trial, and then it needs to be performed a fixed number of times. Each repetition is called a trial. And then the probability of success always stays the same. So in those two mutually exclusive outcomes, we tend to think of them as a success or a fail. I'm looking to see this one thing happening or not in our binomial experiment. And then our notation, we're going to use an n, a lowercase n for the number of trials, a lowercase p for our probability of success, and then 1 minus that if there's only two outcomes. 1 minus that probability is the probability of a failure. And then capital X is the number of successes that we're looking for in n different trials. All right, in this next slide, we're given three different problems, and we need to read through them and see which of them, which one is or is not a binomial experiment. So figure out from the last slide which of the criteria are either checked off or which one is not met. All right, and first I'm looking at A, so maybe you want to pause the video for a minute and write and read through them and think about what your answer would be before you listen to what I have to say, or just keep on listening. In A, we have an experiment with a basketball player. They make 80% of their free throw shots, typically, historically, and they're asked to shoot 3 free throws, and the number of free throws made is recorded. Okay, this one is a binomial experiment. Yes. Okay. The probability of success in this case is that 80% that is mentioned. That's how often they make it. Performed a fixed number of times. They're shooting 3 free throws, and I'm recording how many go in. So this one is a binomial experiment. It checks off all the boxes. Success would be they make the free throw. Failure would be they miss the free throw. So even though they're shooting 3, there's not 3 or 4 different outcomes. It's the success or failure is the making the shot or missing the shot. And then in B, we have people with O negative blood. Based on a simple random sample of size 10 is recorded. According to the American Red Cross, 7% of people in the United States have O negative blood. That one, yes, also. That one is a binomial experiment because fixed number of trials, that's our sample size of 10. We have either a success or failure. So either they have O negative blood or they don't. And the probability is always the same. That's the 7% of people have O negative blood. That letter B, we actually come back to a similar problem in a little bit with more detail. And then with C, 3 cards are drawn from a deck without replacement, and the number of aces is recorded. So you pull 3 cards out, either you get an ace or you don't get an ace for each card. So you have a success and a failure. But one key thing here, without replacement, my probability of drawing an ace changes every time you take a card out of a deck. So because that one is without replacement, that one is not a binomial experiment because of the without replacement. Okay, in this next slide, we will go through a fairly detailed example where we have to compute a probability for a binomial experiment. All right, and we're going to construct the whole distribution for the random variable x. And it's the O negative blood from the last slide. 7% of people in the U.S. have O negative blood. We obtain a simple random sample of size 4, and the number of people with O negative blood is recorded. And we want a probability distribution for that random variable x. Okay, so this is a binomial experiment. What we want ultimately is the probability distribution. All right, so I'm going to draw what that looks like over on the side here. There's an x column and there's a p of x column. All right, so if I have a sample of size 4, I can have either 0, 1, 2, 3, or 4 people with O negative blood. The P of X is what's the probability that no one in my sample has O negative blood, or that one person, exactly one person, has O negative blood, 2 people having O negative blood, 3, or what is the probability, and this one's going to be really small, that all 4 people in my sample have O negative blood. If it's 7% for each person, then it's pretty unlikely that all of them have O negative blood. All right, to show the kind of the reason why we need a formula for this, what we end up needing to do to visualize what our all of our outcomes look like is to draw a tree diagram that represents the successes and the failures and what each trial looks like. Right. So for the first trial, I get the first person in my sample, and that person is either a success or a failure. The success being O negative blood, the failure being nope. Okay, so that's what we're looking at for success and failure. Then the next trial in my experiment, I look at the next person's blood, and that is either a success or a fail, or a success or a fail. That's the second trial. Then we go into the third trial, and that person either does or does not have O negative blood, success, fail. And then we go to the fourth trial. So each of these represent one person in my sample. And then the last trial, there's lots of S's and F's in this one. Success, fail, success, fail, success, fail. Oh, I'm going to have to squeeze these last few in here. Success, fail, success, fail, success, fail. Hopefully you're able to draw this. Whoops, that should be an S. A little bit neater than I am. So you can see here that we have, if you count the last column, we have 16 different outcomes, because those different people can have O negative blood. The success and fails can be arranged differently through my sample of size 4. Okay, so that top row at the top here, so this success, 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 that represents all 4 people in my sample having O negative blood. That's this 4 over here. All right, and that's actually the first probability that we're going to compute. So let me go down here a little bit so I can draw this out. All right, so the probability that X is equal to 4, that our random variable is equal to 4, the probability that all 4 people in the group have O negative blood is the same as the probability of having 4 S's. That's fairly technical. That's not very technical notation there, but that's okay. I'll be a little bit informal here. Okay, so there's this one. I already circled them a minute ago, but I'm going to circle them again. Those 4 S's. All right, and now what is the probability that each individual person in that group has a O negative blood? Well, that's 7%. Each one of those people has a 7% chance of having O negative blood, all 4 of those people. Okay, so what we do is we take that 7%, or decimal point 0.07 in decimal form, and we raise it to the 4th power, multiply it by itself 4 times. That is the probability that all 4 people in the group have O negative. So I'm typing 0.07 to the 4th power into my calculator, and my calculator tells me that it's an itty bitty number, decimal point 1, 2, 3, 4 zeros, and then 2401. Okay, and I'm going to add that number right onto my distribution. Decimal point 1, 2, 3, 4 zeros, 2401. So a teeny tiny number. It's less than 1%. It's less than 1/10%. It's less than 100%. Okay, so a really, really unlikely chance that a random sample of 4 people all have O negative blood. I think it's the rarest blood type. I could be wrong though. Okay, that's one of the 5 numbers that we need for this problem. So let's keep going. Now we need the probability that X is equal to 3. So we're going to go up through this table. All right, probability of 3 successes. Now, find them is the hard part. Here's 1 success in green. Here's 2 successes in green. Here's 3 successes in green. And then I would need a fail. So there's 1 there. And then a success, a success, a fail and a success, that's 2. Now my circling is going to get real messy here. Success, fail, success, success. There we go. So there's 3. And if I go success, fail, fail, I'm not going to be able to get 3 S's out of that. And if you go down to the next one, if you start out with a fail, then everything after that has to be a success in order to get your 3 S's. Okay, so for the probability that x equals 3, that's the probability that I have 3 S's and 1 F. All right, so how many did we find? Well, we found 1, 2, 3, 4 of them. So because we found that there's 4 different ways to do that on our tree diagram, we're going to take and multiply a 4 times 0.07. There's 3 of them now to the third power, and 0.93 to the first power. Okay, because I have 3 people with O negative blood and 1 person that does not have O negative blood. And where did I get the 0.93 from? If you're not sure, I subtracted 1 minus 0.07, or 100% minus 7%. Now type that into your calculator, and you get decimal point 0.0127596. 127,596, and that goes right here. 1, 2 zeros, 127,596. That goes right there in my distribution. All right, so we've got 2 out of 5 spots in our distribution filled in. Let's see if we can do this next one a little bit more efficiently. I don't want to go too low here so you can see it at my tree diagram. I'll stick with the red color scheme. Probability that x equals 2. Now I need 2 successes, 2 failures, and I'm going to look at my tree diagram to count them. 2 S's, 2 F's. I already know, because I need 2 and 2, it's 0.07 squared, 0.93 squared, because there's 2 of each. But what I need is that blue number, and I'll go to blue. How many blues are there? How many 2 S's and 2 F's? Here's an S, here's an S, and then I need an F, F. So there's 1. Here's an S, here's an F, here's an S, here's an F. That's 2. Success, fail, fail, success. That's 3. And what you'll find is there's 3 more in the bottom. And so that I can keep this video from being ungodly long, I'm going to not count the other 3. There are 3 more down there, though. You can find them on your own. So we get a 6 out in front there. Type that one into your calculator, and you get decimal point 0.2542. 806, and that goes up here. My spacing's off just a little bit. I'll move this one up a little bit higher. 0.0254286. So there's a 2.5% chance that in a group of 4 people, a random group of 4 people, 2 of them have O negative blood and 2 don't. Okay, 2.5%. So still really unlikely. These other 2 probabilities better be higher because all 5 of them added together need to add up to 1. All right, again, I'm going to write these last 2 a little bit more quickly. Probability that x equals 1. Now I need the probability of getting 1 S, 3 F's. You can go up into the tree diagram and count them if you want to on your own, but what you'll find is that you'll find 4 groupings with 3 F's and an S. And then now my decimal 0.07 is to the first power. 0.93 is to the third power. Type that one into your calculator. 4 times 0.07 to the first, 0.93 to the third, and you get 0.22521996. So that's a much higher probability. A 22% chance that in a group of 4 people, only one of them has O negative blood. So on our distribution, 0.22521,996. And then the last one, the probability that x equals 0. No one in the group has O negative blood, so the probability of 4 F's is equal to, there's only one place where you're going to find that. I can even circle it. Fail, 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 fail. No one with O negative blood. Everybody with the other blood. Only one spot. And so that for that one, I get my 0.93 to the fourth power. And if you type that one into your calculator, 0.93 raised to the fourth power, you get a much larger percent, 74.8% chance, 0.74805,201. 748. Oops. Oh, what just happened? Sorry about that. 0.74805,201. Okay, so that's my probability that no one. So there's a 75% chance that in a group of 4 people, no one has O negative blood. It's really likely that it's no one, and there's a fair chance that it's one person. Anything beyond that in your group of 4 people, it's extremely unlikely. So, because of that previous slide and the length of that example, that's why we use a formula, because that process of using a tree diagram and counting and doing all that, no, it's complicated to go through all of that. I just made you suffer through it. Well, now from here on forward, let's use a formula. So the binomial distribution formula, this is what it looks like. Okay, P of x, NCx, P to the x, 1 minus P to the n minus x. All right, that's the probability of obtaining x successes in n independent trials of our binomial experiment. Okay, so first I'll just write on top of the formula a little bit. That P to the x is that represents your successes. And then the 1 minus P to the n minus x, that represents your failures. Okay, so if I'm looking for people with O negative blood, P to the x is successes. 1 minus P to the n to the minus x is the people without O negative blood. Okay, and then what I have highlighted there in yellow, that is a button that I'm going to push in my calculator that is equivalent to me counting. We don't go into where this, it's called a combination. You may have seen it in a high school course. I don't know. And it's okay if you don't understand what it is. That's fine. Ultimately, you need to know what buttons to press in your calculator. Okay, and it's equivalent to you looking at the tree diagram and counting how many different ones are the ones I'm looking for. So it's the counting, but we're going to chuck it into our calculator and see what we get. Before we get to the next example, I'll just put this slide up for a minute. Terms that will come up in the problem are these phrases on the left-hand side over here. And when you see one of those phrases, you need to fill in the right inequality symbol, okay? And we'll see that in this next example, what each one means. But, at least is greater than or equal to, no more than is less than or equal to, etc. So if you encounter some of those terms and you're not familiar with them, just look back at the slide and then you'll be like, oh, that's what that means. Okay, now we get to our last example for this section. And in the example, this was taken a few years ago. According to a research company, Pew Research Center, 77% of U.S. adults own a smartphone. I would imagine that number's gone up over the years, but that's what it was when this problem was written. Okay, and that 77%, as soon as I read it, that's terrible circling, I recognize that is my probability of success. I'm looking for people with cell phones in this example. Okay, and then in a random sample of 20 households, what is the probability that exactly 15 own a smartphone? Okay, so I have 20 households total. What is the probability that exactly 15 own a smartphone? All right, so what that looks like, the probability that x equals 15 in my random variable is equal to, now the NCX part of the formula is I have 20 in my sample size, capital C, 15 is the number that I'm looking for. All right. P to the X in my formula is 77% raised to the 15th power. 77 is my probability of success. In part A, I'm looking for 15 people with a smartphone. Then 1 minus P, 1 minus 0.77, is my probability of failure. And then the number of failures is 20 minus 15. Now, things I would personally do ahead of time, I don't like to write down that 1 minus 0.77. I like to do the subtraction right off the bat and write 0.23. Similarly, I don't like to write 20 minus 15 because I can do that in my head, and I write 5. Okay, so that's what I would have done differently if I were doing this problem on my own, because I do this stuff for fun. But that's what the substitution in the formula looks like. Now it's just pushing the buttons in my calculator. So in my calculator, to do that combination, and I'll probably throw a YouTube video up in Blackboard that someone else created just so you can see what this looks like. But I'm going to type in 20, press my probability button, NCR 15 times 0.77 raised to the 15th power times 0.23 raised to the 5th power, and then my calculator spits out 0.1979, 0.1979, or about, let's say, 19.8%. Or about 20%, really, if we round to the nearest percent. So there's a 20% chance that exactly 15 houses have a smartphone out of a group of 20. Exactly 15 have a smartphone. That's part A. Part B, in a random sample of 20 households, what is the probability that at least, okay, so we see that word from the last slide, at least 18 own a smartphone. And for part B, I'm going to need to go down below for a minute, but for this one, we want the probability that X is greater than or equal to 18 in my group of 20. All right, well, how do I do that? For X is greater than or equal to 18, we need the probability that X equals 18 plus the probability that X equals 19 plus the probability that X equals 20. All right? And so we need to compute each of those probabilities individually and add them together. So continuing part B down here, for the probability that X equals 18, I'm just going to write that one out. That's 20C 18, 0.77 to the 18th power, 0.23, that's a 3, to the second power. And then a good check is 18 plus 2 is 20. And we're adding to that probability that X is 19, 20C 19, 0.77 to the 19th power, 0.23 to the first power. And we're adding to that probability that X is 20, 20C 20, 0.77 to the 20th power, 0.23 to the 0 power. And just to save time in your calculator, to the 0 power, that part is equal to 1. So you don't have to type that part in. Just save you a half a second or 3 seconds. Then for each of those probabilities, the first one, you get 0.091. I'm just going to go 3 decimal places. For the second one, you get 0.032. And for the third one, 0.005 for the third probability. Check them in your calculator. Make sure you understand how to enter these into your calculator. But then when you add those 3 probabilities together, 0.091 plus 0.032 plus 0.005, those 3 probabilities added together equal 0.128 or 12.8%. So there's a 12.8% chance that out of 20 households, 18 or 19 or 20 of them all have a cell phone. Now the last part of the section, the last part of this example, and the section actually, we're going to look at part C. And in this one, in a random sample of 20 households, so we're sticking with 20 households, that's good. What is the probability that fewer than 18 own a smartphone? Fewer than. Oops, I lost a parentheses in this one. There we go. Fewer than means less than. I want the probability that X is less than 18. And that at first sounds like it's terrible because I need the probability of 17 and 16 and 15 and 14 and 13 all the way down to 1 and 0. And that would be terrible. So let's not do that. Let's think about this and do it in a little bit more efficient manner. And what we're going to use is the complement. I'll start over here. The complement from the previous section. If I want the complement to this is, well, it's 1 minus the probability that X is greater than or equal to 18. The opposite, 18 or more, we already have that one computed. So let's use that to our advantage. So I can save a whole heck of a lot of time by taking 1 minus 0.128, and that is 0.872 or 87.2%. Whew. So we saved a lot of time there by recognizing that both B and C asked about the number 18. One was more than 18, one was less than or one was greater than or equal to 18, one was less than 18, and that worked to our advantage. Okay, that is the end of this video. Thank you for listening, and as always, let me know if you have questions. Have a wonderful day.